This is problem 92. In this problem, the ball at A is kicked such that the angle for the initial velocity is 30 degrees, so it's kicked at a 30-degree angle. If it strikes the ground at B, having coordinates x is equal to 15 feet, y is equal to -9 feet, determine the speed at which it is kicked and the speed at which it strikes the ground. So we want to find the initial and final speed, and remember that the speed is the magnitude of the velocity. So we want the magnitude of the initial velocity and the magnitude of the final velocity. So I kind of redrew the diagram here. We have the ball going at an initial velocity at an angle of theta sub A, and we have our hill here, and the equation for that is negative 0.04x squared. The ball is starting at the origin here, so where the ball lands, that's equal to x. And then I'm a little bit confused about how they label things in the book for this problem. So when I draw an arrow like this with arrowheads on both sides, I use that for a distance, which should always be positive, as opposed to a vector, which just has the arrowhead on one side. So to me, this says that this quantity should be positive. Now, they label that negative y, which I guess is okay if by that they mean because y is -9, negative y would be 9, but I find that to be confusing. And apparently they find it to be confusing also because when they use this diagram for figure 91, they got the wrong answer. So, in order to avoid confusion, we could say this is the absolute value of y, or what I'm going to do in my diagram is just call the distance from here to here 9. So that's a distance, and it's equal to 9 feet. Okay? And to me, that makes things easier. Okay, and then we could also say because x is equal to 15 feet, the distance from here to here is 15 feet. Okay, now I want to draw a vector diagram like I did for the previous problem. That's using the equation, which comes from our equation sheet, but we got to fix it a little bit because it's not written as a vector equation here. So we'll write it the same way that we did in problem 73 and say the vector delta s, which is the displacement, is equal to v naught times delta t plus 1/2 times the acceleration times delta t squared. Okay, delta s is easy to find in this problem because delta s is the displacement. That vector points from the initial position to the final position. So we draw a vector like this. Oops. And that is delta s. Now, in the previous problem, the object, it was water, the water landed at a higher height than it started from. In this problem, the ball is landing at a lower height than it started from. So you'll see how my method works now for this situation. Okay, we know that this acceleration vector, when multiplied by delta t squared and 1/2, still has to be pointing straight downwards. Furthermore, when I add to that the velocity vector multiplied by delta t, I have to get the change in position. So if we start here with the velocity vector, we have to end somewhere on this vertical line. Now, the initial velocity vector didn't have the same length, but that's okay because this vector that I'm drawing for my equation is not just the velocity, it's the velocity multiplied by delta t. They said the initial velocity was VA, so we'll call this VA times delta t. So that's our new vector there. And then my acceleration vector points straight downward, and I'm just doing this in a different color so we don't get it confused with the 9 feet. So, oops, I don't really want that to be part of the vector. So starting from here and going straight downward, we have 1/2 times the acceleration times delta t squared. After I draw the vector diagram, then I just want to look at the lengths and make some right triangles. In this case, I can make two right triangles again by drawing a horizontal line like this. But now this right triangle is above the horizontal line and this right triangle is going below the horizontal line. So because this is still kind of new for us, I'm going to go ahead and redraw those two triangles, but it's not necessary to do that every time. So this is 9 feet. This is 15 feet because that's the distance from here to here, which is the same as the distance of my horizontal line there. And this is delta S. This triangle isn't really telling us that much because we knew that the ball went 15 feet in the horizontal direction and 9 feet downward. So this is just telling us if you want to find the total distance, use the Pythagorean theorem to find it. So there's not a whole lot of information, not a whole lot of new information for us there. This distance is also 15 feet. This is going to be this right triangle. And the hypotenuse of the right triangle is VA times delta t. I'm not putting the vector sign over the VA. I didn't put the vector sign over delta S either. And so without the vector sign, that would just be the magnitude of the vector, which we can write like this, or we can, for shorthand, just write it like this. Okay, now the question is, what is this side equal to? So if I go all the way from here to here, that's 1/2 times the acceleration times delta t squared. Let's just for short call that the magnitude of the acceleration is equal to g. Remember, g is always positive. Could be pointing downward, but little g is just 9.81 or 32.2 with no negative sign. But that's too long. If I say g divided by 2 times delta t squared, that's going from here to here. So to get this distance here, I have to subtract 9. Beautiful. Okay, so now I have this right triangle here, and I can do a little trigonometry and hopefully find what I'm looking for. So let's see what we have here. We're going to ignore this triangle now because we already said it wasn't very helpful for us, and just look at this right triangle. I do not know what delta t is. I'm looking for VA, so I have delta t here and delta t there, so that's two unknowns. I do know what this angle is because this angle is equal to 30 degrees. Okay, so I have a right triangle. I want to find VA, and in order to do that, I'm probably going to have to find delta t. Okay, so we can always look at the cosine and the sine for the triangle that we have here to come up with two equations. So let's do that. So this is using this triangle here. The hypotenuse is VA delta t. If I take that and multiply it by cosine of 30 degrees, that should give me 15. So that's one equation. Let's call that equation 1. And equation 2 will come from doing VA delta t times sine of 30 degrees. There may be other ways of solving a problem like this, but if you look at the sine and the cosine, that is going to give you equations which are similar to this equation here and this equation here. You might have things on the left-hand side instead of the right-hand side, or vice versa, but that's equivalent to using those two equations. Okay, so now let's see what I have. Generally, for projectile motion problems, I find it always a good idea to solve for delta t. So if you have two unknowns, I would keep delta t and get rid of anything else. You don't have to solve it that way, but generally solutions in the book are done that way, and I like to do it that way as well. So kind of gives you a plan of attack if you always just go ahead and find delta t, and generally I think it turns out better that way. So we have two unknowns in this equation. Now, I could take equation 1 and solve it for delta t, but notice that if you solve for VA times delta t, you can take that and put it in this equation here, and then you'll have gotten rid of the VA. So all we have to do for that is bring the cosine of 30 degrees over to the other side. So we have VA times delta t is equal to 15 divided by cosine of 30 degrees. And then you can take that and put it in here. So that's your VA times delta t. If you did solve this for VA, you would just end up with a delta t in the denominator, and then when you plug it in, it would cancel out with that delta t. So I guess it doesn't really matter if you do it that way. Okay, and then this is equal to g divided by 2 times delta t squared minus 9. You have sine of 30 degrees divided by cosine of 30 degrees, that's tangent. So we have 15 times tangent of 30 degrees is equal to g divided by 2. Oh, let's see, what do we want to put in for g? If we are working with feet, then we're going to say g is equal to 32.2 feet per second squared. We have delta t squared minus 9. Let's just stop for a moment and go back to what we had here. Now, I said we could always do sine and cosine, and that was equivalent to the equations in the textbook, but you can be a little bit more creative. And if you looked at this triangle and said, well, my goal, I know I want to find VA, but my goal first of all is going to be to find delta t. If I look at this side of the triangle and this side of the triangle, I just have one unknown, which is the delta t there. Furthermore, I know the angle, so just from looking at the triangle and ignoring the hypotenuse, you could say tangent of 30 degrees is equal to the opposite, which is 32.2, if we put that in for g, divided by 2, times delta t squared minus 9, divided by the adjacent, which is 15. So we could have jumped right to what we're going to get here when we divide both sides by 15. Okay, so if you want to think about it a little bit and try and find the shortest way to arrive at the answer, you can do that, but if all else fails, you can go with the sine and the cosine. Okay, so we have tangent of 30 degrees is equal to 32.2 divided by 2 is going to be 16.1 times delta t squared minus 9 divided by 15. And we want to solve that for delta t. So actually, I kind of went in the circle there to get what I had here, but now I want to go back and get delta t, so the 15 is going to go back on the other side. So we didn't really need to do that. Okay, so add 9 to both sides, and you get 15 times tangent of 30 degrees plus 9, and then divide both sides by 16.1, and that gives you delta t squared. So to get delta t, you would take the square root. That's going to be plus or minus. When we talked about problem 91, we said if you went back in time, there would be another solution where the path of the ball, if you trace it back in time, intersects the hill. So that's what the negative solution is going to be, which we don't want. We want delta t to be positive, so we're going to choose the positive sign, and we have delta t is equal to, this is going to be 1.05 seconds, which is actually not what we were supposed to find. We were supposed to find the initial speed and the final speed, but now that I know what delta t is, I could take this equation, for instance, although there's other ways of finding VA, and I can say VA is equal to 15 divided by cosine of 30 degrees, and then bringing this delta t over to the other side and putting in the denominator. You now have VA and that is 16.5. Oops, there you go. That is 16.5 feet per second. Now, we want to find the final speed, which is VB. Nowhere in all this work that we have is there a VB. We need a second equation for that. That equation is equation 12.4, but we are going to write it in vector form. So, and let's write it as V final is going to be VB for this problem. V initial is VA plus the acceleration times delta t. We can draw a vector diagram for this equation also. I will do it this time just so you know what it looks like in general, but usually I won't draw the vector diagram for this equation. The acceleration vector has to be pointing straight down. The initial velocity was at an angle of 30 degrees, so we have VA at an angle of 30 degrees. The acceleration vector is pointing straight downward. I need to know how far to draw, how long to make this vector. If I draw it here, then VB would still be pointing upwards. If I make it this long, VB would be pointing in the horizontal direction, but because the y component of the velocity has to be negative or pointing downward when the ball hits the hill, we need to go past that horizontal line, and VB is going something like this. I do not know what this angle is, but it doesn't really matter for solving the problem. Okay, now instead of doing this, you could just use the equations that are given to you on page 41 of the textbook. So the final velocity in the x direction is the same as the initial velocity in the x direction, which you can tell from looking at this picture here. And in the y direction, we have this equation here. So if you want to look at the x components and the y components separately, you can do that. Since I did a vector equation for the first part of the problem, I'm just going to keep going with a vector equation for this also. And I know the speed is equal to 16.5, because that was the initial speed, because I just found that. So if I want to write the velocity, well, looking at what we have here, this angle is 30 degrees. So in the x direction, it's 16.5 times cosine of 30 degrees. So that would be 16.5 cosine 30 degrees I hat, plus in the y direction, 16.5 times sine of 30 degrees j hat. My acceleration is the same as what I had in problem 73. It's pointing straight downward, so the acceleration for projectile motion is always going to be negative g j hat. Do I know what delta t is? Yes, because I found that before. That was 1.05 seconds. So we can put that all together to find VB, but it did ask us for the speed, not for the velocity, so afterwards we're going to find the magnitude of the final velocity. Okay, so we have VA, which is 16.5 times cosine of 30 degrees I hat plus 16.5 sine of 30 degrees j hat plus the acceleration times delta t, so that's minus, what are you using here for g? That's 32.2 times delta t, which is 1.05, and that's pointing in the negative j hat direction. Okay, so we need to know what 16.5 times cosine of 30 degrees is. That is 14.3. And then we need to know what 16.5 times sine of 30 degrees minus 32.2 times 1.05 is. You can do that on your own. This is going to be 8.2 1.25, and the 32.2 times 1.05 is 33.81. There's the negative sign out in front, so that should give you negative 25.6 j hats. So add the I hats together, add the j hats together. We have 2 j hats to add together and only 1 I hat. So that's the velocity, the final velocity. We want the magnitude. So for that, well, this is interesting. Going back to the vector diagram that we have here, this distance from here to here would be 14.3 feet per second. That is the x component of the initial velocity. That is also the x component of the final velocity. And then, whatever this 16.5 times sine of 30 degrees was, that's the distance from here to here. And the negative 25.6 would be the distance from here to here, and this whole piece from here to here would be 32.2 times 1.05. And what we're looking for the magnitude of the final velocity is the length of the hypotenuse here, which is 14.3 squared plus 25.6 squared to the 1/2, and that is 29.3 feet per second. And that concludes problem 92. So we found the initial velocity to be the initial speed to be 16.5 and the final speed to be 29.3 feet per second.